Hi, everyone. Welcome to Lecture 32. What? Yeah, I'm in a different place. I'm down here now from over there. Over there. What? Oh, I know. It's kind of quiet, isn't it? Usually I start with some kind of cool tune to get us in the mood. I don't know. Maybe I won't do that this time.
First I was afraid, I was petrified. Kept thinking I should never sit beside without you by my side. But then I spent so many nights learning to break our key bonds. And I grew strong, learned how to work hard and carry on. So now I'm there, from that space. Now I know just what to do for those alcohols I can't replace. I should have added HBR, I should have made it stop delayed. If I'd have known for just 1 second that I'll wait, 'cause I'm so grateful now, girl. Woke up today, just like someone and now, and you're in napkin no more. Gave me 11 napkin reactions to memorize. You gotta crumble. You think I laid out and died? Oh, no matter, I will survive. Oh, as long as I know physicists can make another high. I've got hydrogen highlights that I can use to synthesize. I'll survive. I will survive. Hey, hey, hey. It's a bunch of my head to get through the hard and try hard to make pieces in my castle box. And I spent so many nights just opening epoch sides. I had a base and take a left, staring me in the side and seeking gods. Make something new, the strongest face in the world can buy the carbon of two. Consider the carbon that you need. E1 for SP and SP2. Well, E2 needs SP3. Walk out the door. Add to the soul now. And ask for his favor no more. What you the one shot making enough all night? Don't you know this crumble? Don't you know the time for a ride? No matter, I will survive. Oh, as long as I got inside me, I know I'll synthesize. And I got all the heat I need. Make cyclohexane out the needs, and I'll survive. I will survive. Oh, going down there, make just one more. Take off the oxygen, 'cause we don't need you anymore. Weren't you the one who tried to equal synthesize? Did you write an AH? Did you write that method for my mind? No matter, I will survive. Oh, as long as I can oxygen, I'll eventually synthesize. And I've got 2 more weeks to live and learn all that God can give, and I'll survive. I will survive. I will survive.
Wow. I thought I'd just show you one of the better extra credit videos that I've seen from Professor Garg's Orgo class out there at UCLA. This is the end. We're coming to the end. This is lecture 32 out of 34. So not much left. This is the whole package. This is it. I thought I'd put them all on this one slide. We saw these 2 reactions in our last lecture 31. We're going to see these in today's lecture 32. And then I know I'm blocking some on the bottom here, but we're going to see those in lecture 33 and 34. And that's it. You will have seen all the sites in Orgoland. Woohoo! Okay. So let's get to today's sites. Some very cool chemistry. And also chemistry that I hope that you look at and see as being very familiar. Okay, and could I even figure out, oh, I could figure this out even if you hadn't read the chapter. Yes, you are that sophisticated. You will survive. Okay, that's our theme for today. So if you were to do this hydration reaction, which sounds all complicated, but basically is just acidic solution in an aqueous environment with a non-nucleophilic acid. So sulfuric acid, for example. Now, the beauty of this is we've learned that this alkene, oops, let's see if we can get this going here, is full of electron density. And so if you throw an alkene into an acidic environment, you have a ton of H+ floating around, and those two are very attracted to each other. Plus loves minus. Yes, every time. And so here is the full blown out mechanism. And notice that sometimes I'll use H+ and sometimes I'll use H3O+. They are synonymous. They mean the same thing. And therefore this reaction can occur the same way. As soon as it grabs this H, this bond goes here and we actually get water back out in an acidic environment. And we create a carbocation. Where does the carbocation want to go? Yes, the same place it always wants to go, because Markovnikov rules. It wants to go on the more substituted carbon. Sound familiar? Good. I'm hoping all of this kind of feels familiar, and that if you had to decide which carbon in this alkene you were going to place a carbocation on, you would pick the more substituted one. Okay? So then we're all set, and maybe the water adds here. Wait, pause, wait, carbocations. What do we always look for when it comes to carbocations? Oh man, yes, rearrangements. Look around, slow down. Do this in slow-mo when it comes to carbocations, because you want to look for hydride shifts, resonance, and methyl shifts. So notice this one will do a hydride shift to put the carbocation on the more substituted tertiary carbon, right? Cool. Now, this carbocation is looking around, please, where's a nucleophile? And if there was no nucleophile, it would do an E1 elimination at this point. But it's floating around in a ton of water. Tons of water as the solvent. Tons of water. Oh yeah, water can be nucleophilic. Yes. So the water adds as a poor nucleophile, but it doesn't need to be good. Just a carbocation screaming for a fourth bond, and it gets one. And I finished off this theory mechanism here with the loss of the H+ off of that water. Remember, this happens at the end of your reactions to end up with your alcohol. And so here's a way that you can take an alkene, and instead of putting 2 bromides on it, Br2, you can put 1 hydroxy group on it and make just an alcohol. Kind of cool. Again, flexibility. That's what it's all about in organolamp. So let's practice. What's the major product for these 2 reactions up here? What would you do? And please pause the video and try it. Ready? Ready to see if your answers look the same as mine? Really, it doesn't do any good if you just wait and see what I got. You gotta get in there and try it. Play around with Orgo. See what products you would generate. This is how you'll build your confidence at the end of the semester here. So, Br2, looking at this alkene, okay? Br2 is going to produce 2 products. two different products. Maybe different, maybe not. But I want you to get the sense that when you do this Br2, whoops, I lost my bromine. Hold on, come back, bromine. So when you do this reaction, you start with an alkene. So here's my alkene, okay? Everybody see my alkene. Now, it can be drawn like this. So you can see the four groups coming off that are all planar to each other. Or I can turn it sideways a little bit and point the groups out at you as wedges and dotted lines and show you the double bond. I want to hold it like this to emphasize this, that here's my little Br2, okay? Br2 can come down and start adding to the double bond on the top, or it can come from the bottom. I can form my bromonium ion in two ways, top or bottom. And this actually will create different stereochemistry. The regiochemistry is going to be exactly the same, but I might get different stereochemistry. So please be aware of this, okay? What about now if I just add H3PO4, phosphoric acid, and water, or an aqueous phosphoric acid is sometimes how you'll see it. The products here would be the same idea slightly, but that when you add the phosphoric acid and protonate that alkene, this double bond is going to pop open and get protonated. There's my little H, and protonated, and leave behind this little 3-bonded carbon that is now planar. And now the water can come and add from either the top or the water can add from the bottom. So again, I get the same regiochemistry. Everybody adds to the same regions of the molecule, but from top or bottom, I might get two different stereochemistries. So that's why I posed this question to you. What term would be best to describe these two major products that are formed in these two reactions? Should I answer it now? Nah, that would be too easy. So for lecture 32, this one, I'm going to answer this question at the beginning of our lecture 32 class that meets, okay? And I will record it and post it on our Sakai site for those of you who can't make our class. But come to the class, see if you can tell me what you think the answer is to these, and then I'll just sit there and say, yes, you were right. Because I bet you're right. Okay? Cool. Now, what about alkenes to halohydrins? Whoa, there's no subtle transition to this. This is just kind of a combination of the two ideas that I just presented on the last slide. What if you did the addition of bromine, this Br2, for example, to your alkene, but you didn't do it in a solvent like carbon tetrachloride, CCl4, something as innocuous as that, but you put your bromine in with a bunch of water. Wow, what would happen? You would make yourself a halohydrin. So they're really cool. So let's talk about the mechanism of this a little bit. Notice the bromonium ion is still going to form. Could form on the top like this one is on the example up above, or I could come from underneath and form the other stereoisomer. But if I form this bromonium ion, then Br minus is usually what normally would react here. But hold on a second. That Br plus makes this feel like a positively charged epoxide. This carbon, one of these two carbons, is going to be very partially positive. And the thing it's looking for is a pair of electrons that's closest to it. Please Give me a pair of electrons so I don't have to be Br plus anymore. I don't have to be a bromonium ion. And so if you surround your bromonium ion with tons of water, water everywhere, then the first thing this bromonium ion is going to bump into is a water molecule. And the water is going to act nucleophilic at the most substituted carbon and do everything that our positively charged epoxides did when attacked by a nucleophile. They would attack in an SN1 regiochemistry, but do SN2 stereochemistry from the backside and produce this beautiful product. Again, I'm showing you the whole workup of the loss of the H plus because O plus is awful. You don't want that O plus over there. That's nasty. So, and I'm not sure now, I'm on the bottom. I'm not okay, over there. Up there, you don't want O plus. So off comes H plus in this process. But when you get done, you have created a beautiful bromo hydroxy bifunctional group, otherwise known as a halogen hydrin water OH, a halohydrin. What's so cool about halohydrins? Well, now you don't have just two bromides on your molecule or just one OH on your molecule. Now you have a bromide and an OH, two different functional groups. One that's a very poor leaving group, one that's a very good leaving group. And so now you can do some amazing chemistry with those that's separate for both, that might not have been able to be done if you did two bromides or only one hydroxide. So halohydrins are very, very useful. They're very useful for one other reason as well. Did you spy it? Have you spied it? The other reason they're useful is because they are a precursor, the molecule right before I make that product, that epoxide. That epoxide is now useful to do other chemistry with, right? And let's go over how and why. Maybe you see it already, but as I mentioned, you got one good leaving group, one bad leaving group, but a possible nucleophile. So cool. So halohydrins are generated so that you can then add and create, say, it doesn't have to be a bromohydrin, it could be a chlorohydrin like this. And notice the stereochemistry on these two. Remember, bromonium or clinorium ion comes on one side, like the top, and the water comes from the opposite side. So we get them in opposite directions. So here is our halohydrin. Now you do one more step. All you do is add a little base, just a little, because this reaction is so favorable that even though this hydroxy is not acidic and does not want to have its H plus pulled off, the second one little H plus is pulled off, we have a negatively charged oxygen right next to an electrophilic carbon, right here. That's really with a great leaving group. So this intramolecular reaction happens so fast. I drew the arrows because I couldn't wait for the arrows on my slide. It happens so fast that you will actually make this final epoxide. And notice the stereochemistry of it is, it's coming backside attack and pushing off the chlorine. So it does have certain stereochemistry. But the goal is, you've now made an epoxide, which we saw from our previous lecture. You can do an acid opening of the epoxide or a basic opening of the epoxide, and you can then take that and go off into Orgoland in all sorts of different directions. So these are very, very cool reactions because they allow you to go off in lots of different directions in your Orgoland map. Okay?
This is a test. This station is conducting a test of the emergency broadcast system. This is only a test. This is a test of the emergency broadcast system. The broadcasters of your area, in voluntary cooperation with federal, state, and local authorities, have developed this system to keep you informed in the event of an emergency. If this had been an actual emergency, the attention signal you just heard would have been followed by official information, news, or instructions. This station serves the metropolitan Boston area. This concludes this test of the emergency broadcast system.
Whoa! An emergency epoxide system. How cool is this? We've just gone through all this rigor of how to make an epoxide. Why bother? You can make an epoxide with one step, one chemical. Notice, you take a peracid, which is these funny little molecules that have these OO single bonds in them. They look like carboxylic acids, but they have one extra oxygen. And you've experienced peracids before. There's hydrogen peroxide, maybe in your own house. Okay? These are very strong oxidizing agents, or bleachers, as we know of them. But I will never ask you to show me this mechanism. I just thought I'd show it to you now once to prove it to you that it can work. Notice this peracetic acid. This peracetic acid and all the arrows that go with it, you throw this one peracetic acid molecule in and out pops your epoxide. So cool. And a more stable peracid is the metachloroperbenzoic acid, the mCPBA. So we'll be using this acronym a lot as mCPBA. And then you start with any alkene, you put in mCPBA, boop, emergency epoxide maker. Cool, you just made an epoxide in one step. Phew, very, very cool reagent. Thought I'd show you that one. Okay, well, let's play. What if I wanted to make an epoxide out of this alkene? How many different ways have we learned to make epoxides? So let's summarize. All right? Pretty cool. Just in our emergency epoxide maker, mCPBA, throw it in, and you will get a racemic mixture of this epoxide, because the mCPBA can attack the alkene. Let me reform my little alkene here. Take off that H. Remember, it's planar, and mCPBA's mechanism is that it sits down on top of the double bond, mCPBA, and creates the epoxide here. Or the mCPBA could attack from the bottom, pushing these groups up, and form the epoxide pointing straight down. These two will generate two different epoxides that have two different chiral centers. So in this molecule, we would get a racemic mixture. What else? Oh yeah, the other one, remember the peracetic acid? I don't know, that one's harder to write. There's no abbreviation for it. So on paper, I'm a big fan of mCPBA. mCPBA, woohoo, epoxide maker. Okay, sorry. I'm too excited. Can't help it. So is that the only way? No. Remember our halohydrin. So we could add and create our halohydrin with a little bromine and water, okay, and produce this halohydrin, and then throw in a little base, and pop, out comes our epoxide. So now we know how to make epoxides, halohydrins, just hydroxyl groups, alcohols off of a double bond only, or dibrominated. We got lots of choices. And in our next class, we'll start looking at the last few reactions we have left in Orgoland. So I'm getting kind of sad because really there's so much more, but we've kind of run out of time. So I can't wait to see you again. I hope you're all healthy and well, and stay safe, stay sane. See you next time. Bye.